Hi, I'm Rowan Bailey. I'm doing a PhD at Imperial College at the moment. I've been working in photochemistry for a short while now. Within the department, my main role is to do research and also to help build this group that is under Phil Miller and Mark Crimin. As part of that, we've collaborated with Asynt to try and bring in some technologies and supplement our photochemical research. The main area of research that we've been looking at is photocatalytic carbonylation reactions. So generally speaking, that goes from carbon halogen bonds and takes them through all the way to either amides or ester functionalities by inserting a carbon monoxide unit from a gas cylinder, so a headspace of carbon monoxide, and then subsequently we can functionalize that group to sort of close the loop. Mainly we've been looking at cobalt catalysis to do this because it's both cheap and readily available. It's very earth abundant. And so as part of that, we've been optimizing the process, developing new methodologies and hoping to really redefine this area of photocatalytic carbonylation. The Illumin8 has been really pivotal for our work, actually. So something that many people struggle with, I think, in this space is reproducibility. And certainly that is an ongoing challenge for photochemistry and photo research. Within our space, the Illumin8 made a huge difference because it both added robustness and reliability to the process, and we actually ended up leveraging that in a big way. So we did kinetics of our reaction, and this is something that is very challenging for photo reactions because of this inherent variability. The kind of consistency that the irradiation brought us while using the Illumin8 had a big impact on those kinetics, and actually allowed us to connect this very robust data set and subsequently understand our reaction much more deeply by doing that. And this is something that's really quite on the forefront of photochemical research at the moment. Kinetics are a big challenge for conventional chemistry and an even bigger challenge still for photochemistry. So I think the Illumin8 was a really big impact for that and giving us that trust and robustness to kind of generate this data set. I think between the two lights, we have to be considerate of the safety concerns with shorter wavelengths. So first of all, we were especially cautious when using UVA, for example, versus the slightly longer wavelengths. But in terms of the chemistry, we were actually using a range of them. So for example, when you use slightly more fundamental photocatalysts like 4-CZ-IPN and so on, they tend to use longer wavelength LEDs to excite them. And we've definitely been doing that research within our group. But equally for the carbonylation reactions that I mentioned prior, we're mainly using UVA, and it allows us to do this quite high energy transformation. Because they're all contained within the Illumin8 very nicely, there's not much risk of escape, which is fantastic. But it certainly is true that we had to consider extra precautions with the slightly more hazardous light, but nonetheless, we've been able to do a whole range of different chemistry using the different wavelengths and their necessary sort of application cases. Imperial has been making quite a large effort towards sustainability in recent years. I think it's something that's ongoing and challenging all of us, especially in the chemical sciences. So recently, Imperial has made a large commitment to LEAF certification within all of the groups in this building. So within our postdoctorate labs or postgraduate labs, this LEAF certification is essentially an evidence that we are committed to reducing wastage and enhancing our efficiency during our research. And that's something that we need to consider every single day as researchers. I think Imperial are encouraging us to get this certification, and they have goals and milestones in mind, which is fantastic. On top of that, there certainly is a desire to buy less and waste less. I think that the chemical inventory system that we use, which is called LabCup, really encourages us to speak with our peers and borrow each other's chemicals where it's appropriate, because what tends to happen quite routinely is people build up a big stock of chemicals where perhaps somebody needed a chemical for a reaction of 1 mil, but they bought 10 mil. And so that 9 mil is potentially at risk of being burnt or put to waste. So the chemical inventory system is really encouraging us to use chemicals where they're already available to us rather than buying more and building this stock of chemicals that are ultimately going to be wasted. Stepping into photochemistry was quite a big step for our research group. I think doing photochemistry and equally some of the electrochemical things can really help with sustainability of our chemical reactions. Using energy or for light or electricity directly is a fantastic driving force for us because we can generate this from renewable sources. So for doing photochemistry in our group, I think that we've seen a big improvement in sustainability, both in the kind of reaction media we're using. We're tending to use much cleaner, greener solvents, but also the fundamental idea of using photochemistry to drive and produce energy driving forces for our reactions has been fantastic. And I think the biggest evidence for that is the fact that we can use earth-abundant catalysts for this transformation, where carbonylations are generally run by palladium in the thermal cases. So it's allowing us to be greener with our catalysts, it's allowing us to be greener with our energy usage, and again, using greener solvents as well. So I think that stepping to photochemistry and using a reliable photoreactor has given us so much scope to start thinking about these headings. Within photochemistry, as I mentioned already, there are some challenges in robustness and generating procedures that are generally reproducible across research peers and across multiple sort of labs. So I think by doing a visualized experiment submission, we can try to cut through that limitation, and by demonstrating exactly how we're doing our procedures, being as transparent as possible, we really have an opportunity to create robust methodologies that others can also use. So in the terms of using our chemistry for application and for other people developing our chemistry further, I think the opportunity to show exactly what and how we do our procedures is really important. You know, the convention is to write our experimentals in our supplementary information, and of course this is a really important thing, but I think that we could all agree that the words that we use are not always clear enough, and actually generating a visual example of how we do our reactions is a really fantastic thing for enhancing the robustness of our science, and as I say, allowing others to reproduce and continue enhancing our science further as well. There's so many wonderful opportunities within photochemistry to continue to improve and enhance our sort of methodology capabilities. I think for myself, I'm very interested in recycling waste products, especially those that could be environmentally harmful. So I think within photochemistry, there's a unique opportunity to do endergonic reactivity. So that is uphill reactivity. And in this case, I'm hoping to leverage that to activate carbon-fluorine bonds for functionalization. So carbon-fluorine bonds are some of the strongest that we know of, and they can be incredibly challenging to activate. But within photochemistry and with photosensitizers, we have an opportunity to functionalize them and turn them in from waste products that are likely to end up in landfill or just the environment more broadly to actually incredibly useful building blocks for pharmaceuticals. And that's the real interest of mine moving forward. And I think that towards the conclusion of my PhD, that will be the research I can conduct.